Hi everyone, it's Prof. K speaking, and today we're going to talk about colligative properties. So our learning objectives for today are to practice expressing concentrations of solution components using mole fraction and molality, which is a new sort of version of concentration I'm going to introduce in this video. We're going to describe the effect of solute concentration on some solution properties, such as vapor pressure, boiling point, freezing point, and then in a separate video, I'll discuss osmotic pressure. And we're also going to perform some calculations using the mathematical equations that describe these colligative effects. And so I'll start with introducing these equations, and then we'll work on these equations together in class. So what are colligative properties? Colligative properties are the properties of a solution that only depend on the total concentration of solute species and not on the species composition. So for example, a property that isn't a colligative property is acidity. Because if I give you 0.1 molar of HCl, and I also give you 0.1 molar acetic acid, it doesn't matter that they have similar concentrations because HCl is a strong acid and acetic acid is a weak acid. So the resulting solution is going to have a different acidity. Viscosity also heavily depends on the intermolecular forces between the particular compounds and will not have the same, if you change from HCl to acetic acid, you might have a different viscosity as well. Or if you change from sugar to HCl, you're definitely going to have some different properties. Density, similarly, is dependent on the species that is present and not just on the concentration. However, there are some properties that only change as a function of concentration. So examples of this are we can lower our vapor pressure based just on how much we add of something different, if that something different isn't volatile. Our boiling point similarly changes for similar concentrations of materials. Our freezing point changes, and our osmotic pressure changes as a function of concentration. And so all of these are properties that only depend on the concentration of what we've added to our solution, and it doesn't matter what it is that we added. So to start, we want to think about how we describe concentration in the context of colligative properties. Because so far, we typically use molarity to talk about concentration. And molarity is equal to the moles of solute per the volume of solution. But we spent time last semester, and we're going to talk about it more in this course, discussing how the volume of a particular solution can change as a function of temperature. So if this volume is dependent on temperature, it can be hard to make sure that we're talking about just the changes in concentration that come from these colligative properties. And we really want to focus on how concentration is affecting these colligative properties. So we have another way of expressing concentration or describing concentration, which is molality. And molality is the moles of solute per kilogram of solvent. And the reason this is useful is because neither moles nor kilogram of solvent. So I have these expressions switched. So here, this definition for molality should be up here and vice versa. So molality is moles of solute versus kilograms of solvent. And neither of these depends on anything other than the amount that we've added. So we're really talking about what we're interested in with the colligative property. Another way that we can describe concentration or relative amounts of a solute versus a solvent is using mole fraction. And what this is we represent it with this XA, or the mole fraction of A, and we define it as the mole fraction of A versus the total mole of all components. And so today, when we reference the concentrations for these colligative properties, what we're going to use is molality and mole fraction, because this more specifically tells us how our amounts of solute versus solvent relate to each other, and it's less dependent on the experimental conditions that we're operating in as molarity. So the first colligative property I'm going to talk about is how vapor pressure lowering is relative to just the amount of some non-volatile solute that we add. And so I just have on the slide that vapor pressure lowers relative to a solvent vapor pressure if we add a non-volatile solute. And so if you like, you can pause the video and think for a second, why do you think this might be the case? Or can we relate this back to our conversations about surface tension or intermolecular forces, or sort of what do you think? So hopefully you had a second to think about that. And so one of the main reasons why this vapor pressure lowers is because as the solute disperses in the solvent, it's entropically favorable and it stabilizes that solution and makes it harder for liquid to leave the gas phase. And if it's harder for liquid to leave the gas phase, then there ends up being less vapor or less vapor pressure on top of that solution because it's harder for the liquid to leave the gas phase. And we can specifically say what the partial pressure will be of any given component for an ideal solution. And the way that we can describe that is we can say that the partial pressure coming from one particular component is going to be equal to the mole fraction of that component multiplied by its original vapor pressure. So we can see that the vapor pressure we end up experiencing is some combination of the solute vapor pressures. And if we had something that was non-volatile here, it would just be some mole fraction of the original solute, which would be the vapor pressure. So we've lowered it by multiplying the original vapor pressure by a fraction, if we're talking about something soluble or non-volatile. And we can ultimately describe the total pressure on any given solution as the sum of individual vapor pressures multiplied by mole fraction. So like I said, if one of my compounds is non-volatile, and we'll say that its mole fraction is 5% or 0.05. Then if I'm talking about my final vapor pressure of my new solution, it's going to be 0.95 times whatever the original vapor pressure of the solvent is, which means, sorry, it's not working. Oh, vapor pressure of the solvent. So this causes it to lower. And the only reason it lowers is it has a lower concentration, which is why this is a colligative property. And when you lower the vapor pressure of something with the addition of a solute, then we have to be raising the boiling point because you're going to need a higher temperature in order to get your vapor pressure to equal the surrounding pressure of whatever system you're in. So the lowering of the vapor pressure causes this raising of the boiling point. And once again, it's only related to the concentration of the liquid, of the two components or of the multiple components, because that's the only thing we're changing about our particular system. And this boiling point elevation can be described, so we can say that the change in temperature is going to be the result of some boiling point elevation constant, which is based on the solvent, as well as the concentration of whatever solute you're adding to it, which could vary, and you'll still see the same change in temperature. And this M here, this lowercase m, is the molality of our solvent species. So this expression allows us to describe for a given solute, how much will your temperature change with different molalities? And this is very useful because you can, for any system, if you want to add HCl, if you want to add sugar, if you want to add salt, no matter what you add to the system, we can see that we get the same change in temperature for a particular system. We can also see that if we look at the freezing points for these systems, that we see a similar freezing point lowering with the addition of any solute. And it's a very similar expression where we have the change in the freezing point temperature is going to be equal to some freezing point depression constant, which depends on the solvent, not the solute, and the molality of the solute species. And something that's important here is this is the total molality of all solute species you add. So if I wanted to add 1 mole of HCl to one solution, and then half a mole of HCl and half a mole of sugar to another solution for whatever reason, they will have the same freezing point depression for that change in temperature because ultimately I added 1 mole of something to the same amount of solvent. So my molalities or my total molalities will be the same for both systems. So this is further sort of proof that the freezing point depression is going to depend just on how much we add of our solute and not on anything that has to do with what type of solute it is. And in particular, freezing point depression is something that you might have encountered in your own life if you've ever used salt to de-ice something, or if you've ever tried to change the temperature or lower the freezing temperature of something by adding something else to it. And so it operates based on this colligative property. And we can summarize the changes that I just discussed as a phase diagram in the solution. So if you compare the freezing point of your solution to the freezing point of the pure solvent, it lowers in temperature. Sorry, the pen isn't working very well today. And if you look at the boiling point of the pure solvent versus the solution, you raise in temperature. So you can see sort of the shifts in how we reach different boiling points, and you can see the changes in temperature on this plot, and potentially also the change in pressure that results from this change in temperature, and this shift in property based on the fact that you've created a solution of some material. And so this is just sort of a more diagrammatic way of talking about these changes. We can also look at how electrolytes impact colligative properties. So in theory, if we have something that dissociates like salt, we can expect to see Na plus and Cl minus. And if you have something like hydrochloric acid, you would expect it to completely ionize to form H3O plus Cl minus. So we would predict that we would have complete dissociation for these strong electrolytes. However, when we actually record the differences in boiling point, vapor pressure, and freezing point, it seems to suggest that these aren't completely dissociating. So we're not getting twice as big of a change from concentration like we would think we would have based on the fact that it splits into 2 ions or 2 solute molecules. And so the way that we describe this process and how it works is using a Van Hoff factor. And so the Van Hoff factor is we have this I, which represents the moles of particles we actually have in solution versus the moles of formula units dissolved. So for NaCl, we would expect that for every 1 formula unit we dissolve, we should get 2 particles, so our I should equal 2. But what we find is our I actually equals 1.9, or it's only partially dissolving. And why that takes place is because when we dissolve these compounds, which we suspect are strong electrolytes and which act as strong electrolytes, so the reason that we see incomplete ionization or dissolution is that while the inner ionic attraction in a solution is mostly screened by the solvation of these water molecules, it is possible that there are temporary ion pairs that form in water and they reduce the apparent concentration of our solute, even if we expect complete dissolution. And so the way we describe the actual concentration that we observe for our ions is activity. So activity is the effective concentration of these ions, which informs what we get for our Van Hoff constant, which we'll practice using.